Okay, so here's an interesting problem. Read through it, do your best to solve it, and then press play when you want to go through it with me. So, sorry, I apologize for the crude drawing here. It's hard to make nice straight lines in the program I use. But essentially, what's happening is this object is starting with some initial speed and at some height. And as this object travels, it doesn't mention anything about friction here, so we're going to assume there's no friction. There's no friction. The only forces acting on this object are gravity and the normal force as it falls. Okay, so because those are the only two forces, and in this case the normal force is not doing any work. The normal force here is always pushing perpendicular to the track, and the object is always moving in the same direction as the track. So the normal force is always perpendicular to the direction of motion, which means the normal force is not doing any work, which means the only force that is doing work in this case is gravity, which means we can use our very, very simple equation, Ki plus Ui equals Kf plus Uf. Mechanical energy is conserved in this case. So however much mechanical energy we have up here is the exact same amount of mechanical energy I'm going to have when I'm right here, and it's the same amount of mechanical energy I'm going to have right here. So Ki plus Ui right here has to equal, K plus U right here, which has to equal K plus U right here. And that's how we're going to figure out how fast it's going at all those different points. So I'm going to pick three different events in this case. My first event I'll just call my initial event. That's when I'm at a height of 100 meters. My second event I'll call A, and my third event I'll just call B because that's how they're labeled. So I want to figure out how much mechanical energy do we have at that initial event. That's going to be equal to K initial plus U initial. So I can write my total initial mechanical energy is just 1/2 mv initial squared plus mg times y initial. V initial is the speed I'm going at this event, and y initial is the height of my object at this event. I don't know what m is. M is an unknown variable. And that's okay because it's going to show up in all my expressions for these other events, so it's going to cancel. So for now, this is how I'm just going to leave m as an unknown variable where I've now plugged in for v initial and y initial. And then here I've solved for my total initial mechanical energy in terms of m. So it's 1430 times m, whatever that is. This total mechanical energy is going to be constant. It's constant in this case because the only forces that are doing work is gravity. So this total amount of energy has to be the same energy that I have at this point. So let's look at what's happening at point A. My total mechanical energy at point A is equal to the kinetic energy at point A plus the potential energy at point A. And my kinetic energy at point A is just 1/2 mv, my speed at point A squared, plus mg times my y position at point A. My total mechanical energy is conserved, so however much mechanical energy I have beforehand, which is here, has to be equal to the mechanical energy I have at this point, because mechanical energy is conserved in this problem because the only force doing work is gravity. So I can set 1430 times m equal to the expression I have here, and here I've plugged in for my height. My m's cancel because they show up in every expression, every term. And then I can solve for v sub a. That's going to be the speed that I have when I'm right here. And finally, I can do the same thing for b that I've done. And I put in my height. Y sub b is the height that I'm at when I'm at the point B. And then I can plug in here, again, the m's cancel, and I can solve for v sub b.